I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video where we are looking at the mechanism involved in brominating a ketone. Halogenation reaction involving ketones. Everything I'm showing you here applies equally well to aldehydes. Here I'm specifically focusing on bromination of a ketone as our model for this video in an acid catalyzed environment. Can this reaction occur and why does it occur? What is the end result? Let's look at it. Again, we're looking here at a ketone with bromine, diatomic bromine, Br2. In an acid environment, we have here dimethyl ketone or acetone. Now, when you're looking at this reaction, the halogenation of aldehydes and ketones, it occurs by means of three steps. One is enolization, where you have keto-enol intermediate. The other one is your bromine attack. And then lastly, you have a deprotonation. We will look at all of these. Deprotonation means a proton will be lost or a hydrogen atom is lost. We are starting here with the enolization step number 1. When you're looking at this, you have in essence a item here as your starting point, which looks like this. The oxygen has 4 electrons, and this reaction occurs essentially at the alpha carbon. But you have 2 alpha carbons. The carbon directly adjacent to your carbonyl is always an alpha carbon. You have 2 alpha carbons. The hydrogens attached to that are alpha hydrogens. Here we have 2 alpha carbons and we have 6 alpha hydrogens. But for the purposes of this video, we're ignoring this methyl group and we're focusing over here. I have a methyl carbon here, which is alpha carbon. Then I have a hydrogen here, which is an alpha hydrogen. We're only focusing on 1 alpha hydrogen, even though these are equally alpha hydrogens and so are these. But our essence of the reaction is on that hydrogen. Keep in mind also that when you are looking at this enolization, it's your rate determining step. If that step occurs, everything occurs. If it doesn't occur, everything will stall. And it depends on how basic this oxygen is. You have something here which can behave as a Lewis base in electron pair donor. If this oxygen can donate this pair of electrons easily, then this reaction will occur. And the way it can do so easily is that there's a surplus of charge coming into the oxygen. If these groups attached to your ketone or aldehyde are electron donating, and it helps. If they're electron withdrawing like trifluoromethanes, then that would be a non-ideal situation. And then in that particular case, these electrons here are not going to be donated because you have electron density being pulled away by these fluorines, which are highly electronegatives. The more electropositive or donating these groups are, the better your reaction will be. With electronegativity coming into the picture, it spoils your reaction. Step number 1 doesn't occur. So the better these groups are, the better it is. You could even have a situation where you're looking at something like this, and here you have cyclohexane rings which are even more electron donating than methyl. So this is even preferred than something like this. Then you can have methyl groups attached to this, which is even more preferred because now you have excess charge density coming into your carbonyl. We're making this even more easy to behave as a base. So you have to keep all of these things in mind. The better these R groups over here in terms of electron donating, the better this entire reaction. Methyl are fairly good, so we can proceed with that as our model. When you have this oxygen behaving as a good base, then this reaction will occur. But how is it going to behave as a base? And let's talk about it. You have this acid. Let's remove this acid H+, and we'll bring it over here. You have hydrogen ions in the solution. This oxygen is going to look for it and it seek it out. 2 of its electrons will be used in generating the oxygen-hydrogen bond, and you will have CH3, C double bond O, H. 2 of those electrons have been lost and it's CH3. Oxygen always likes to have 4 electrons or 2 pairs of lone electrons. Here you've lost 2 in generating that bond, and when you've lost that natural state of oxygen, you'll bring a positive charge over here. This is where we are. Now let's bring in that alpha hydrogen and let's focus on it. I have a CH2 over here and then I have my alpha hydrogen. What will happen here is this carbon hydrogen bond will sacrifice itself and you will get rid of that charge deficiency here on this oxygen. This alpha hydrogen will drift away. Now I've developed here a carbon-carbon double bond and I have exactly everything as I'm seeing it, and oxygen is back to its 4 electrons and it loves it, and that's what it wants to have. What we have over here is an enol. We have here a keto and here we have an enol. Why is it a keto? Why is it an enol? Because here you have a ketone group, you have a carbonyl group. Why is this enol? Because you have an alcohol and an alkene. Here's your alkene, here's your alcohol. So this right here is called your keto-enol intermediate. This whole set of steps over here is called enolization. If this occurs well, because the oxygen can behave as a base, then you've overcome that rate limiting step and you can go to the next step, the bromine attack. So this is where we're at. Now in the bromine attack, let's talk about it. What happens? In the bromine attack, and keep in mind this hydrogen has come away as a proton and we're not worrying about it anymore. In the bromine attack, you have a diatomic bromine, and you would think that two equally electronegative atoms will share this bond and they will be a non-polar covalent bond and there's no polarity, but you would be wrong, or you'd be surprised to determine that this is a very polarizable bond, because at any given time, because of the atomic sizes of both of these and instantaneous dipoles, one can be partially positive, one can be partially negative. You know each bond is represented by 2 electrons, and this one bromine can just pluck it away and making this electrophilic. You could end up having an electrophilic bromine and a nucleophilic bromine in the same molecule, Br2 diatomic. The pi electrons from this bond right here, you know, double bond, has a sigma bond and a pi bond. The pi bond electrons, or the pi electrons, will search out for this electrophilic bromine, and 2 of these electrons from this double bond will generate a carbon-bromine bond, and you'll end up with this CH2 and you've developed a bromine bond, and you still have everything else as you see it, as I'm showing you right over here. Remember, you had a double bond, the pi bond electrons have generated the carbon-bromine bond, and everything else will exist as you are seeing it. This carbon here will have a positive charge as a carbocation because it was having electrons from this bond, but it's lost. Those electrons have come right here, carbon bromine. This bromine which plucked the electrons away is going to drift away as a bromine anion, as you can see, a negative charge, and we won't worry about it any further, but I'm erasing it just for cleanliness. That Br2 has split into a nucleophilic bromine, which I won't show you any further, and the electrophilic bromine, which has developed this bond. The essence of this halogenation reaction is you develop a carbon-bromine bond at the alpha carbon. Now we have to do something about this. The enolization step has occurred, the bromine attack has occurred because your bromine-bromine bond is very polarizable. Your pi electrons from your pi bond can search for that electrophilic bromine and add it, and the other bromine drifts away, and you do this. It's called a bromine attack, even though bromine is not attacking it. Your pi electrons are attacking it, but it's also an electrophilic attack of bromine on the alkene. You can word it differently and it's still the same. The electrophilic bromine is attacking your alkene, or your alkene pi electrons are attacking your electrophilic bromine, where your alkene pi electrons are behaving as a nucleophile. Either way you word it, it's still correct. So this is where we're at. These 2 electrons over here can come over here and donate to this deficiency in the carbon, and this is a step which can reverse on itself, and you can end up seeing an intermediate bunch of reactions, which would be exactly what I'm showing you over here. You're developing a carbonyl and you have this right over here and your CH3, and this is where we are. Now this deficiency, the lack of octet, has been sufficed or completed by oxygen donating back its 2 electrons to generate that. Remember, oxygen loves to have 4 electrons. Here we're back to 2 electrons, so I have to bring a plus over here. Now the only thing which remains is step number 3, deprotonation. This proton has to go away and sacrifice its involvement in this bond, so the bond electrons can come and satisfy the oxygen and give it back its 4 complement of electrons. And I will show it to you right here on the top after erasing these. In the deprotonation step, this hydrogen will go away. The 2 electrons of this bond will come right over here and satisfy oxygen in terms of its positive charge over here and return everything into a normal state for that oxygen, and you will have this. You see, you got your 4 electrons back. These 2 electrons from this bond have given you those 2 electrons, and you have your end result over here. This hydrogen right here, it'll be a byproduct, which is your plus H plus, but it regenerates your acid catalyst. Remember, we had H plus over here, which I brought over here. The acid has been regenerated from that deprotonation step, and everything is good. What is the end result of this halogenation reaction? A alpha bromine located on your ketone or aldehyde. If I were to do this reaction once more, Br2 in the presence of acid, can I add another bromine? Probably not, because this electronegative bromine is pulling charge density away. These oxygen electrons are no longer very basic. You may not be able to see that step 1 enolization, the rate determining step, occur easily, and the reaction will halt. The more electronegative these atoms and these oxygen electrons are not as basic, and the reaction cannot proceed, and it stops right here with a single bromine being added to your aldehyde or ketone. Remember again, here's your enolization steps. Here is your bromine attack step, and then right here is your deprotonation step right over here, as you can see. And that right there is pretty much all we're showing you for this video. Thank you for watching.